All right, we're in Windows world again, building 26. Introduce yourself, please.
I'm Silviu Calinoiu. I'm the lead for the user mode analysis team. It's the team that actually analyzes all these crashes that come from users from all over the world.
Aha!
So if you see those pop-ups, they come to us.
See that face, ladies and gentlemen? That's where those pop-ups go. Now, one of the things you've been working on for Windows 7 is the so-called Fault Tolerant Heap. Can we talk about a little bit what that is and how it works? Like how did you make it fault tolerant? I hear heap, it's memory. Can you talk about what's going on?
So first of all, I think it's interesting to understand why we did it and
yes.
what we did it. So my team analyzes all these crashes,
yeah.
Lots of them, and there are so many that we always try to slice and dice them and classify them, because otherwise we won't be able to deal with this massive amount of stuff. So, and one class of issues are heap corruptions. And at some point, it was probably 3 years ago, I was curious to understand, out of all these crashes that we receive, how many are actually heap corruptions. And so we have infrastructure here in our database servers. Every dump that comes from customers is actually information about symbolic stack trace and stuff. It's uploaded in the database. So I can answer questions like, what percentage of all the crashes in the world have a particular function on the stack? So then I said, well, the most conservative way to define a heap corruption is a crash where I have some heap management function on the stack. Because this usually means that we crash somewhere in the guts of the heap manager because it cannot deal with whatever corruption is in there. And it's a conservative way to approach things, because many times the corruption happens and then a couple of milliseconds later you crash in something totally different. So it doesn't cover everything, but anyway, we did this, and the number we discovered was staggering. 15% of all the crashes have heap management APIs on the stack.
Interesting.
So then the next thing, so that's one point that went into my brain. The second one is, my team is also responsible for engaging third parties to fix these bugs. I mean, I'm not sure if many people realize, but the majority of things that we see here are not Microsoft issues. We need to engage companies from the ecosystem that develop software. And so what I realized, by doing it, is that it's really hard to fix some of these bugs, because it's not like in Microsoft where you finally figure it out and you make a check-in and the next day you get a bill with a fixed binary. It takes time to find the right person at that company. It takes time for the person there to understand the bug and fix it, and then another big thing is, even if they fix it, it takes months until the fix reaches all the machines in the ecosystem.
Yes.
So there are all these steps. It's very possible for a bug that you understand here to take a year until it actually hits a majority of the machines affected by it. So that's the second point. And the third point is that heap corruptions are very hard to debug. Many times when you crash later, after the stuff already happened. I mean, the damage inside the process space was already done. So, and it's very difficult to figure out why you are in that state. I mean, what's the root cause of it?
Exactly.
You know for sure that, okay, something is really broken here, but you have no idea what's the root cause for it. So those kind of the third thing. And so out of all that, I thought that it would be interesting to have a version of a heap manager that in a very conservative way tries to detect these errors and continue them. So if there is an error that can cause heap corruption, and it's a very contained thing that we understand and we can safely continue, then we will do that. So that's kind of the fault tolerant part of this, that's what comes in the name. The other thing, which it's not in the name, but it's actually very important with this project, every time we do this, we collect diagnostics. We get stack traces for what we mitigated in there, and all those things will get back to Microsoft. And they are easier to debug than a heap corruption crash.
Excellent.
So it's the fault tolerance that will, well, I call it, I mean, I like the word self-healing, so I could call it like...
So do I. Homeostatic, man. Very cool.
Yeah, so it gives some sort of self-healing degree to applications, but it also collects all these diagnostics that are generate more debuggable issues that with which we'll also engage third parties and try to fix all these bugs. So the point is not really to not fix these bugs, just like make them disappear because for fault tolerance. It's just buy some time until we actually fix them. So we fix them, but also we try for that year that I was telling you about, where it takes until the bug gets propagated in the ecosystem, we offer some fault tolerant behavior.
So let's talk a little bit about that, because it certainly, a lot of times, I mean, as you really very well know, obviously, I mean, the heap corruption could happen, it could be just a random occurrence, right? It may never happen again.
Right.
It could be the way things were interaction, you had something happen strange in memory done by some other application. I mean, it's hard to know. So the question I'm trying to blurt out, or is how do you determine what the patterns are to say that this is going to be, oh, we recognize this, we can keep on going? Where does that quote unquote intelligence live, and what's
Right.
going on?
So the interesting thing with this project is that almost every decision was driven by data, because we are sitting on this mountain of crashes. So every time we made a decision, it was based on analyzing this data, which is great. So what we did actually, there is another project I worked on 5-6 years ago. You may know it, Page Heap.
Okay.
So I was at that time I was the main developer for Page Heap, and in Vista there is a feature where through Watson settings you can ask a customer to run with Page Heap on for a process. It's not very used, but I mean, you need to know a lot of stuff to use it. So only some developers inside Microsoft actually use it. But based on this, we had a project called Corruption Harvester, where we enabled for high traffic Internet Explorer corruption buckets, this Page Heap on customers. We collected 1,000 CADs or so, and we analyzed all of them, and we classified the kind of heap bugs that we discovered. So we knew kind of clearly what are the types of bugs that need to be mitigated, and there's no surprise. It's buffer overruns, it's double freeing, it's touching a block after being freed, it's freeing stack variables, it's freeing globals, and it's freeing a block in the wrong heap. That's a kind of, and those are the high traffic ones. There was another one where you free a biased pointer. So instead of freeing the address that was returned by alloc, you free an address that's plus 4 bytes. And it comes out of a typical way COM B strings work. They're always biased by 4 bytes. So we knew exactly what kind of bugs we need to address.
Okay.
Um,
But I mean, let's take the buffer overrun
Right.
example. I mean, clearly you're not. I mean, how do you mitigate that
Right.
in runtime context?
Yeah. So what we did, so that's one thing with FTH. We don't try to do crazy stuff. It's only it's very conservative at this point. So what happens is buffer overruns. Pretty much we add padding to all the blocks. So if the block looked like this before, when FTH is on, the block will have an 8 bytes of padding, and there is also an FTH area after the padding where we keep some juicy information, including some magic stamps here and here. So every time the buffer overrun is contained within this area, we say, oh, okay, so there was some damage, but it's contained. Nothing else was broken. We'll just take a stack trace so that we can know about the bug and debug it. But other than that, we just continue. If it's more than 8 bytes, then we'll just pass it to empty heap and let it behave as before. So that's kind of one of the principles. Is if we can do something that's conservative and safe, we'll do it. Otherwise, we'll just let the process behave as before. Mm-hmm. So one thing with FTH is that it gets enabled only after an app has a bad behavior. I mean, it crashes. We don't get enabled for an app that's very happy. Mm-hmm. So it's only after the app experience crashes and stuff like that that we intervene. So that's one of the principles. If we can contain it, fine. Otherwise, we'll just let it rip as before. Mm-hmm. And really, in terms of mitigation, so I enumerated all these bugs that we can mitigate, heap bugs. But really, there are three main, actually 4 techniques used by FTH. So one of them is that we zero all the blocks. Every time you allocate something, it will be zeroed by default. There are lots of bugs related to that, so it's good for good mental health to zero the blocks all the time. So that's one thing. The other thing is padding. So this deals with small buffer overruns. Mm-hmm. The third thing is delaying freeze. And I'll come back to delay freeze, but the other thing that's interesting is not freeing at all during shutdown. So I'll talk about this because it's simpler, and then I'll come back to delay free. So it's also driven by data. What we discovered when I asked that question about how much is heap corruption and all these crashes, I was also curious how many of these things happen during process shutdown. And it's a question that I knew will have an interesting answer, because I know that process lifetime is kind of like airplanes. The worst moments are takeoff and landing. So process startup and process shutdown are very prone to, there's a lot of stuff going on, and they're very prone to crashes. And in particular, at shutdown, there is a frenzy of freeing. I actually did once experiment with, while developing FTH, I did an experiment with IE. I just wanted to know in Internet Explorer how much stuff happens, and from the time you hit the close button until the process actually exits, there are like hundreds of thousands of frees going on in there. So it's just a frenzy of object destruction. So the answer I got was that out of all the crashes that happened during shutdown, process shutdown, 30% had heap management APIs on the stack. So 30% of the shutdown crashes are heap corruption. So I said, you know what, we'll just not free anything there, because they happen during free. Okay. So yeah, I mean,
So to be clear, though, you said that a few times. I may want to make sure that's clearly understood. These are, when you talk about heap APIs on the stack, you're talking about the heap manager,
Yes.
things that the heap manager does. So I rely on the heap manager to do things for me,
Right.
correct?
Yeah.
That's what the heap manager is supposed to do, is manage the heap.
Yeah.
So when you're saying 30% of the time you're seeing faults caused by the heap manager itself, or are you saying things that called into the API? Can you make that clear for
Yeah.
those who don't program this every day?
So it's almost never the case that these are things due to the heap manager. These are not bugs in the heap manager.
Sure.
It's just that when the heap manager maintains a lot of internal state about what's available, what's allocated, all that stuff. So and usually this metadata is kind of intertwined with user data, the blocks that are returned as a result of a malloc or operator new. So whenever you have buffer overruns or you touch areas that you already freed, it's very likely that you will poke in this metadata and you'll confuse the heap manager whenever it tries to allocate new blocks. So typically a crashing stack may look like this. It's some third-party code that eventually will call free or operator delete or something like that. And this eventually will call RTL free heap, which is the heap manager function inside NTDLL that actually implements the anti-heap manager. And then there may be a couple of internal heap manager functions here, and then there will be a crash.
Okay.
So the trick with the tricky part with this is that it's not it's almost never the case that the guy who called free here is at fault. So it's definitely not the heap manager bug here, but it's also not the fault of this guy, because everything is shared. So it could be that the corruption that triggers the crash here was done a couple of milliseconds before by somebody totally different that lives in the same process. And that's especially the case with processes like Internet Explorer that are extensible. So you have all these
plugins.
Yeah. So in IE, media player, all these hosting processes, it's really hard to debug these things. Yeah.
Interesting.
So coming back to delay freeze, what FTH does, whenever you free a block, it will not actually be freed. It will be kept alive for a while. So the way it's organized, we have a delay-free queue of blocks that has a limit specified in megabytes, which is the sum of the blocks being delayed in here. So whenever, right now in RC the limit is 4 megabytes. So 4 megabytes worth of frees are kept alive. And let's say the queue is full and you free a new block, you will go to the end of the queue and will start chopping blocks from the beginning.
Okay.
So this queue, depending on the dynamic in the process, it can buy you a couple of 100 milliseconds of delay.
Okay.
And this is useful because most of the time these bugs, and I'm referring here to double freeze and reuse after free. So both of them are a sort of touching the block after being freed. Either you free it again or you try to read or write in it. And imagine if you write in a block that you already freed, it could be that that block was already allocated to somebody else. So at that point you are writing into some innocent...
Exactly.
Yeah. These bugs tend to have a sort of temporal locality. It's most of the time it's the case that only within a small window these things will happen. It's not that you free the block and 5 minutes later you'll free it again. It's usually this kind of, because they typically come from races between two threads racing to do the same operation or things like that. So a small window like this can buy you some time. And by the way, it depends on the dynamic in the process. For example, my usual testing victim for this was Internet Explorer. So
hey,
poking.
Good.
So if you are cruising in Internet Explorer, just like you uploaded a page and you're kind of like clicking around, you can get 100, 200 milliseconds here. It's still a lot of allocations are going on, but you get this time. But for instance, during shutdown of IE, because of that frenzy of freeing that I've told you about, there's a lot of stuff going on in here, and this window becomes smaller. Just to clarify, I said that we are not freeing anything during shutdown. Mm-hmm. So, in principle, this would contradict with what I said here about the queue. Well, it's just about what's the definition of shutdown.
Yeah, exactly.
Right. So, for us, definition of shutdown is whenever you call the exit API. Or the internal version in NTDLL, which is called RTL exit user process.
Okay.
So whenever the process calls this, we consider the process enters shutdown, and from that moment we don't free anything.
Okay.
But between clicking on the close button in IE until you do the exit, there's pretty much an eternity of stuff happening. So when I said that the window gets smaller, it's between these 2 points in time.
Understood. So I mean, it's the application itself during that time slice is actually cleaning up state, doing what it needs to do, storing user data, whatever an application has to do because all applications implement their own close functionality.
Right.
You're talking about from the standpoint of the platform that lets this craziness run in user mode. It waits for that signal to go, okay, you're done with your stuff, let's rock and roll on our end.
Yeah.
So I understand what you're saying. That's really interesting. But do please clear up a little bit of the not free again. So when the exit is called in the Windows API, you're saying you're not freeing.
Nothing. From the moment this is called, every time you call free, it will be a no-op.
Got it.
Yeah.
So real quickly, the heap manager we've talked about on Channel 9 before, Adrian Marinescu.
Yeah.
So I want to state, hey, Adrian, don't be offended that I might have said there were bugs in your code. It's just that I heard the APIs on the stack, and I was like, wait a minute, what's going on here? So I just had to get that out there, because Adrian's a nice fellow.
Adrian's code is squeaky clean.
He is a rock star, man, for sure.
Yeah.
All right, let's continue. I'm sorry.
Yeah, so the other thing to clarify here is that this does not replace the anti-heap manager. It's not a full-blown heap manager. It's just a layer on top of anti-heap. So what we do actually, we use this shim technology that's used by AppCompat to replace, to rewire API. So pretty much what happens, this stuff that I described is implemented in something called FTH shim, FTH AppCompat shim. So what happens is, whenever you say to something called the shim engine, the AppCompat shim engine, you say, please apply this shim to this application. What the shim does, it declares APIs that it wants to rewire. In my case, it will be all these heap manager APIs, RTL free heap, RTL allocate heap, and a bunch of others.
Got it.
And the shim engine, whenever the application starts, it will rewire it so that whenever somebody calls RTL free heap or all the other ones I'm interested in, instead of calling the original API, they will call me instead.
Got it.
And I have the choice when I get called to either do some stuff and then call the original API, or I may choose to implement completely the whole thing. But FTH doesn't do that. It just decorates the block or delays the free or things like that. but in the end, it will call the original anti-heap manager to do the actual allocations. So just to give an example, whenever you allocate a block, what we do, we say, okay, you want 14 bytes, but we want to allocate the padding. We want to allocate this suffix block here for FTH heap. So we get a different size, a bigger size, and we call anti-heap manager to allocate this stuff. And when we get it back, we put all the magic stamps in all the right places, and then we return the block to the caller of the API. So it's always just decoration, but in the end we use the anti-heap manager. So
sure.
Yeah. Yeah. So that's pretty much the FTH shim. There is another thing. So FTH is actually composed of two things. It's this shim. There is also an FTH service. So the idea here is, okay, I have this nice shim that does fault tolerance and stuff, but when do I apply it? I mean, who decides?
Exactly.
So that's the purpose of the service. It's the one who implements the policy.
Okay.
What it really does is to monitor crashes in the system. It looks at all the crashes that happen, and it will ignore crashes that do not look like heap corruption, and that is defined in a very conservative way. Right now, a crash looks like heap corruption if it's an access violation in NTDLL, or it's a heap corruption exception, which is C0374. AVC gazillion 05. So this is clear heap corruption because it's an exception raised by the heap manager. So it's a clear heap corruption, no doubt here. This one is a little bit, it may include more than heap corruption because not any access violation in NTDLL will be caused by heap corruption. You know, it could be, that you try to initialize a Unicode string and you pass a null buffer or something like that.
Okay.
So it's a little bit generic, but not by much.
Okay.
So FTH service looks at only this kind of crashes. So
okay.
I noticed this in discussions. People think they hear this fault tolerant or self-healing and they think, oh my gosh, my game was crashing in Vista and now it will just work in Windows 7. But if it's another type of crash, FTH will ignore it. In a way, we're testing the waters with this self-healing idea. So I wanted it to be as crisp as possible and kind of conservative. So it looks, but on the other hand, remember that these crashes represent 15% of.
Yes.
So we're talking about many.
So you're hitting the sweet spot. You're just not
right.
going to the fringe cases, which that's
right.
not the point. I mean, that's not what you.
Yeah.
It's very interesting.
Yeah. So the service looks at all these crashes and. It has two possible behaviors. So there is an autonomous behavior where just locally will make decisions when to apply FTH. And the way it does that, it calculates, it's kind of a pompous name, but we call it crash velocity for an application. So it's something that it's expressed like 4 crashes per hour. So every time an app crashes, FTH service starts tracking what stuff is going on with that application.
Okay.
And if the app manages to crash 4 times in an hour, which is a pretty awful experience,
Absolutely.
it will apply FTH.
Okay.
But
But again, just so people understand, because not everybody watching this is going to be, a Win32 programmer, and they don't really live in this world of thinking about double freeze and whatnot, because they're writing managed code, which is memory managed in the real sense. Yeah. Not in the real sense. Don't get me wrong. In a different sense, because you don't double free. You don't deal with those kind of problems, right? It's all taken care of by the garbage collection system. So let's talk about. So I wanted to be clear here. of exactly what you mean by when I call your fault tolerant heap because I've crashed. So take us through. Crashed 5 times in an hour.
Mhm.
Take me through what it means the next time I run, that instead what's going to happen is you then assume control versus your little layer, and then you proxy me to the heap manager doing your magic.
Right.
And then you, assuming then that my app just stays up if you understand what the errors are.
Right.
Is that what's going on here?
Yes.
All right.
So the moment you crashed 4 times in an hour or 5 times in an hour, actually you won't manage to crash the 5th time because after 4 FTH will be applied.
Cool.
So the moment FTH is applied to our application, let's call it text.exe, right?
Mm-hmm.
You launch it and you start running. Every allocation or any heap operation will go through FTH, and FTH will decorate the blocks, delay the freeze, and whenever it's proper, you will call the anti-heap manager to do the operations.
Mm-hmm.
And we keep track of bugs that we mitigated in here and continued. And every time you exit your application or you crash, the service actually keeps statistics of did we do any good or not. Mm-hmm. Because that's another thing that's important. And it's important because the service, and it's something that I like a lot and I actually fought a lot for it. It doesn't ask any questions. It will just apply it. So
excellent.
Because, I mean, the typical argument, how am I going to explain to my mom mm-hmm. that I need to apply a fault tolerant heap to her cooking
her cooking website.
Right.
Amen. You're absolutely
right.
correct.
So, but this autonomous decision comes with a burden, which is that now you cannot pass the bug to the user saying, hey, you said yes, so you have to observe if it sucks behavior and turn it back. So we need to observe if we don't make any difference and go back off, Mm-hmm. So that's why the service keeps track of what happens when a process exits. And it's really very simple. What we do is maintain for each application something that we call an FTH ticket. Every time a process exits, we update the ticket based on some simple results. So what matters is did the process exit cleanly or crashed? So those are 2 distinctions. And the other thing is, did we mitigate anything or not? Did we detect any crashes, any bugs in there that we continued? Okay. So the only thing that's considered a clear success is if we exited cleanly and we detected something. Because then we assume, that's probably because we did something good in there. There was a bug that previously was creating corruption and now it's contained. And so in that case, the ticket will go up by 1.
Okay.
It's a ticket, so whenever the service enables FTH for an application, you will get an initial ticket value, which let's say it could be 16. So every time a process for that particular application, this ticket is maintained for each application distinctly. So every time a process for that application exits or crashes, we update the ticket. Eventually, if you will go to 0, we will disable FTH. It means that we didn't do any good. So now to come back to this matrix, so if you crash, no matter what, we consider this FTH failure.
Sure. In
the sense that, yeah, okay, we didn't make anything better in there. It's probably the bug was not didn't have wasn't of the nature that it's detectable by us,
mm-hmm.
And so we'll just make it -1.
Which of course brings up a good question, in the sense that if I'm running IE, just to keep picking on IE, because it's fun, but I'm just kidding, Dean and company, I love IE. But just to use the example that you've been testing, right? So, just because the application crashes 4 times in an hour, the crash could actually have nothing to do with heap corruption, in which case your service would never be called, right? So let's say IE keeps crashing because a plugin does some sort of AV that's outside the scope of the ones you're looking for, right?
Yeah.
Application crashes 4 times.
Right.
Then, next time I launch it, is there any data to tell you that, hey, you know, this thing's crashed 4 times, but we don't know whether or not it's due to a potential heap corruption, so do I load your service or not?
If the crashes, those 4 crashes do not fall into these rules, the service will not trigger at all. Yeah. By the way, I mean, you can do some registry magic to change these things. Yeah. But right now, yeah, I mean, for instance, you can express things like every time there is an AV anywhere, apply FTH. So you can tweak it if you want as an admin, but
sure.
At this point, I don't feel like.
We won't talk about that. I mean, the point is, I was just trying to reiterate the form of asking a question, that you have sort of a broad yet scoped functionality.
Yes, it is.
Even though a lot of stuff happens on the heap in Windows, right? There's a lot going on.
Yeah.
Anyway, I just wanted to throw that out there. So
yeah, that's actually a good point. So, and it comes from the fact that I really wanted to have a very controlled experience for the first version of this idea. Sure. Be conservative and just kind of only things that we're almost sure they are safe to do. We'll do only those.
Great.
So here, this is considered a failure at this point. So if you exit without mitigations, we say, okay, it used to crash, now it exits. So probably we did something good, but we're not sure. So right now we'll just, the ticket will go down and eventually we'll back off. So this is something that probably need to play with to see exactly. So that this would be one area where we can become bolder, you know.
Now, of course, this data, if I choose to be, I mean, I think it would be really useful for you specifically, because you're part of the, just for people to understand, you're part of Michael Fortin's broader group of Windows 7 efficiency and telemetry and diagnostics and all this really interesting stuff.
Yeah.
Adrian now works on this team as well.
Yes.
So, in that context, because you have the diagnostics infrastructure, the telemetry infrastructure, when something like -1 in the upper right corner happens where you exit without mitigation, that data could be very useful for you personally.
Yes,
to understand.
We squim everything about this stuff. We know for every app, we know exactly how many times we fall in any of these things.
Perfect.
And it's actually quite interesting because by now we looked at beta data, we looked at RC data for this, if you look at particular apps, it's all over the map in terms of the fault tolerance part. The diagnostic part where we send bugs to Microsoft, that's clearly, we get lots of data. But
sure.
The fault tolerance part, we have clear apps for which life is definitely better with FTH on. We have apps where it's kind of a mixed thing, and we have apps where we don't seem to do any good at all. It's clear that for those, these crashes are not due to the type of heap corruption that we mitigate in here. It's something else. So, by the way, this reminds me. I forgot to mention here. So I mentioned the autonomous.
Yes.
There is one other thing. The FTH service, whenever it sees a crash for an application, it will ask the mothership here if we have anything to say about that application. And so you can make Watson settings here, Watson bucket settings, that can have three possible, you can say three possible things for application name and application version. You can say, yeah, don't bother with this crash velocity, just enable it right away, and the FTH ticket should be 50.
Okay.
Or you can say, please do not touch this application at all. We know already through previous debugging that it doesn't help, FTH doesn't help. Or you can, the answer coming from Watson servers can be, I have no idea, do your crash velocity thing and decide by yourself.
Okay.
So the reason I'm saying that is, it's definitely that this FTH system will have to be used with us here actually looking at the SQUIM data and actually turning knobs up and down for various applications. So it will be the case that based on SQUIM data we'll find out that some number of applications this doesn't seem to help. So then we'll just make Watson settings here that say don't touch those applications.
Sure.
What we'll do though for those, we'll probably use it, so it's clear that we don't get fault tolerance, but we'll try to do random debugging, statistical debugging on them. So what will happen is probably for brief windows of time, maybe an hour, a week or something like that, we'll just enable it, FTH, so that if we detect some bugs, those come to Microsoft. Because every time, so let's say an app crashes, you know, if it crashes but it crashes with mitigations, those stack traces are still very juicy and interesting for debugging. There are still bugs there. So even if you don't make a difference, it's interesting to collect these things in order to collect bugs. And by the way, these heap bugs are really nasty bugs. Most of them are exploitable, security exploits. So it's really important to know about all these things.
Yes.
So
now listen, it's great that you brought that up. I mean, the C++ compiler team, which of course you guys use to compile Windows,
yeah.
I just talked to Louis Lafreniere, the WAC-GS++, compiler switch, which will go through your code, obviously, and mitigate and let you know when it encounters a number of buffer overrun possibilities, classic string buffers, but also in certain types of structs that just hold data that was exploited. So people out there, use that, man. So mitigate that stuff up front, because memory is where hacking begins and ends, man.
Yeah, yeah.
So anyway, you mentioned that. I had to throw that out there. It's a very, very useful compiler tool.
Yeah.
Compiler switch. Anyway.
Yeah. So one other point that I wanted to mention is, so what happens in this case in terms of collecting bugs?
Yes.
So you exit successfully. By definition, well, not by definition, but the normal behavior is we get dumps that get sent to Microsoft only when you crash. Well, with FTH on, actually we generate a dump even if you exit successfully, as long as we detected bugs in there. Because what happens is every time we collect a stack trace for a bug, we save this in a blob of FTH blob of data. It contains all these juicy stack traces there, and whenever the process exits, we actually generate a dump. It's something that is done quietly. I mean, you don't see any pop-up or anything.
Sure.
But we collect a dump that will get sent to Microsoft, so that we can debug all these issues and classify them.
So let me ask you a question, though. Since this is an extra level of abstraction and over memory operations, does a user experience the 5th execution attempt for the crashing Firefox? Because I'm going to stop picking on Internet Explorer. You know, the Win32 application that's having memory problems.
Yeah.
do they detect it running a little slower? Is there anything visible to them where because we don't let them know that something's happening?
Right.
But I mean, it's a fair question. I mean, there's overhead here. How
Right.
much is there?
The overhead is real. Definitely, we use more memory. Every block has roughly 32 extra bytes.
Okay.
And there is also the delay-free queue that uses 4 megabytes of committed memory, so it has some overhead. Very likely you will not see it as a casual user,
Okay.
but if you are a performance guru, you will not. I mean, if you run benchmarks, you will notice. So, for example, we did some benchmarks. It's definitely not the most scientific performance, but we use some harness to see what's page load upload time with and without with NT-Heap Manager and with FTH for Internet Explorer. We didn't do it for Firefox.
Okay.
And it went for typical pages, like we tried CNN.com and OVA and stuff
Sure.
like that. It went from average of 1 second to 1 second and 200 milliseconds. So this is 20% regression. So it could be, I mean, it could be significant, but it's something that will show up only in something that's very performance intensive, where you really pay attention to these things.
Yeah.
Probably not for a normal user.
Sure.
Casual user, just browse.
Yeah.
So yeah, there is a performance.
Which is, I mean, in some sense, it's diagnostics.
Yes.
And that's really what's going on here.
I mean, yeah, in a way, if you think of it, so this thing triggers only if you have an awful experience.
Yeah.
So you are probably at a point where you really don't care that much about being fast. You just want to stay alive,
Yeah, sure.
So
let me ask, one of the cool things you guys have done in Windows 7, particularly, partially on this team, but also obviously with the WEX group, the Windows Experience people, is the Action Center, right? So when you're talking about, if I'm running an application, let's say I'm running Chrome, just to keep things really fair,
yeah,
and it's corrupting heap for some reason. Who knows what's going on. Crashes 4 times. On the 5th time it runs, you collect all this data, and then it turns out you're able to go out to the internet with a nice software plus services, the non-marketing software plus services, the useful stuff.
yeah,
You go out to a service, you collect some information, come back, oh, it turns out that this application, you need to install a patch, and there's a patch available for it on this website that we won't name. Very cool, man, because again, it's all about efficiency. So you figured out the problem.
yeah,
You solved the problem in 2 ways. One, you put a Band-Aid on the problem for long enough for me to keep on doing what I needed to do.
yeah.
And then you actually got me real information about what I actually have to do to fix the problem so that you don't ever run again in this situation.
Yeah.
It's just, I have to say, I mean, Windows 7 efficiency to me is one of the most incredible things about what's been done in Windows.
But it's amazing that you brought this, because it's one area of the design that I obsessed a lot. And if you think through this FTH ticket logic, every time you apply a patch that actually fixes the issue, FTH will naturally disappear. Because the moment you apply the patch, you will start getting into this situation here. Exit without mitigations, because you just fixed it. So this means the ticket will go down, so in a few process runs, it will just disappear and you will just run with your patch.
Excellent.
So that's it's actually amazing that you focused on that particular
Yeah, well, I mean, it's just part of connecting the dots, right? Putting things together. I mean, people sometimes will get caught up too much in the fact that we focused on this one little, actually in some cases big. It took you a long time to figure all this out and write all this code, and debug it and get it to work in the system, but as you step out farther and farther, you see that it's really part of a pretty amazing effort to just stay out of the way of the user until you need to get in their way.
Yeah.
Let me get what I need to get done. Give me the information I need when I need it, right? So it's going beyond the marketing crap that you see, like when you install Windows, right? It's a do what you want faster, make yourself better, blah 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 blah. No, this is reality.
Yeah.
We're going to run faster. We're going to be more efficient. So I love it, and this is one of the reasons why. I mean, you're doing smart engineering. Very cool. So what else have we missed? I think people kind of hopefully understand by now what this is.
Yeah. Well, one thing I wanted, I hope it's appropriate for this, but I wanted to mention the names of the people who worked in the team.
More than this is Channel 9. It's all about
Okay.
humans, man.
So it's not only me, it was also David Grant,
Okay.
worked on development, it was Pavan Kasturi and Anthony Lorelli who tested this,
Nice.
and Will Campbell who did the program management for this.
Excellent.
So,
So there were 5 of you.
yeah.
Very nice, man. Very cool. And I'm sure you asked some questions. You'd go hang out with Adrian, get a cup of coffee, and be like, hey, man.
Yeah, well, I had long conversations with Adrian
Yeah.
about this stuff, and actually with a couple of other people.
Yeah.
I'm not sure if you meant Jen Kergan.
No.
Yeah, he's an he works also for Mike 14. And,
Okay.
yeah, he's.
Some of these guys won't come on camera, you know.
Try Jen, he's good.
Yeah. All right.
Yeah, lots of other people helped with this. The security guys.
Sure.
So I went through, after I implemented the version, they actually very thoroughly reviewed the code and I had to scrub it. So the main point was, in Vista, you probably know the anti-heap manager went through a big improvement so that it's very hard for hackers to exploit bugs.
Yes.
So there are all these cookies and scrambling and stuff. So what I wanted with FTH, since now we sit on top of anti-heap, we don't want to turn the clock back.
Mm-hmm.
So I went through the security review so that we use exactly all the techniques that anti-heap uses in order to avoid the exploits. So now FTH does all these things like cookies and scrambling and
Nice.
checking flinks and blinks in double linked lists and all this
Wow.
stuff. So yeah,
That's
so
hardcore. So let me ask you a question. Are you writing C or are you writing C++?
C.
Okay, see, this is something we don't talk about enough. It's still amazingly interesting how much C is in Windows.
Yeah.
Not just C++.
Well, I mean, it's probably because I'm a dinosaur, but well, so yeah, I mean, it could have been C++ easily, especially this one. Just, I'm not sure if you looked at the code in the kernel. So I'm a product of the development team that was led by Dave Cutler.
Yes.
So in the sense that, you know, I read their code many times, like, you know, Landy Wang, Dave Cutler, all these great guys. So for me, I mean, that code reads like a beautiful book, you know. So
Yeah.
I love it. So
Excellent.
so that's where I'm coming from. So, and that code it is actually C, but it's kind of object oriented in the sense that, you know, it's not inheritance and all that stuff, but everything is well structured as object. When you describe the design, it's very easy to speak about 3-4 objects and how they pass messages between them. So everything is very clean and crisp.
Excellent.
So, you know, in a way, this one is C, but it's kind of like, I mean, in spirit, is object oriented, you know. So, which is probably the most important thing, in a way, just to have this. Yeah, so it's C.
Perfect, man. Yeah, because I was going to say, there's a lot of cool sort of tools and libraries that could be used in the C++ world that are new.
Yeah.
You know, safe int, for example. I know that's used all over the place in Windows. That's created by David LeBlanc. He's on Channel 9 today. Came out of his cave to be on Channel 9. He's not really a big kind of camera person, but that's the only reason I brought that up. It's also because it's nice to know what's going on, right? It's nice that clearly there's a lot of C
Right.
happening.
So there is one other,
Sure.
you mentioned at some point the managed applications.
Yeah, .NET.
So in my experience, every sizable managed application, and I'm talking like production, like for example eHome.
Okay.
So all these big applications, almost guaranteed, they are not pure managed code. There are all sorts of reasons for that. I mean, it could be that a particular dark corner of the functionality needs to be super duper fast.
Mm-hmm.
So then they make the decision, okay, we're going to implement this in C++.
Mm-hmm.
So whenever you veer into unmanaged world, you are prone to these heap corruptions.
Sure.
And actually we see it in our feedback system. So we see applications that are managed and have lots of heap corruption.
Well, again, that's because they're interoperating with COM.
Yeah.
Or, you know, remember, obviously, the CLR is a native application.
Right.
I mean, so perhaps there's some CLR bugs you may have helped discover, but in the case that you're talking about, absolutely. You have to interoperate with COM if you want to do win forms, for example, right? That's what you do, right? You're interoperating with Win32. You have the wrappers around Win32 APIs that you call into, and blah, blah, blah. But of course, Raymond Chen never makes any mistakes, right? There's Win32 APIs.
Probably not.
Yeah, he's
pretty good.
He's a rock star, man.
Yeah,
But he won't come on Channel 9 because he's afraid, he's scared, he's shy. Anyway, man, awesome to talk to you. I think this is really, really cool, and I hope that
It was a pleasure talking to you.
Yeah, man. I hope it continues to give you really good data.
Yeah.
And we'll see what happens in the future as it evolves.
Yep.
Perfect.
Thank you.
Great job, man.
Thank you.